Okay, so in this video, we are going to be creating random samples again, but this time just a limited amount instead of 10,000. We're not going to try to basically build a sampling distribution, but what we're going to do is show a little bit more about this concept of confidence interval. So we're going to build 20 random samples and then compare these 20 random samples and the confidence interval we can build around them to be able to show practically on a figure what 20 samples with confidence interval, how do they relate to the mean of the population or the data set we're using as the population. So first of all, we're going to use again a repeating loop. So we initialize a step counter. What I call index here is going to be basically a vector that stores number 1 through 20 just to set the 20 repeats that we want to do of the for repeating loop. We're going to store each sample into an object called TemporarySample and store the results into results 120 that will contain the mean, the lower and the upper value of a confidence interval based on a normal approximation, as if our data set, like we've done since the beginning, is the whole population and it's a normal distribution. So we're going to repeat the loops. So again, 20 times using the index object that stores the number 1 through 20. We're going to take a temporary sample of size 120. Size 120 represents 10 years of data, for example. We could set any different size that we want, by the way. And we're not going to replace the object, so we don't have a chance of selecting 2 times the same record from the object CO2 data that we created a few videos ago and that we've been working with for the last few videos. Then we're going to calculate the sample mean. We're going to calculate the lower confidence value using the normal approximation, the upper confidence value, and then store these 3 values into our object results 120 in a column mean, lower, and upper. So this is the for repeating loop. We repeat for I in index. We take a temporary sample of size 120. We calculate the mean and store it into the mean column. We calculate the lower value of the confidence interval and store it in the lower column of the results 120 object or data frame, and then calculate the upper value. So this is only 20 samples, so it's going to be really quick. Now we can take a look here. Could have had a visualization with a histogram of each of these, but we've done that in the video, so I'm not going to do it. If you want to do that on your computer to observe these different things, feel free to add histogram of the temporary sample, for instance. Then what we're going to do, we're going to create a plot that shows each of these 20 samples, the mean of them. So we're going to do a dot plot with the means. On the x-axis, we're going to have the value of the mean in ppm CO2. And in the y-axis, it's just going to be sample 1 through 20. So we don't necessarily want to show that y-axis, not very useful. Now, in here, I'm saying, we want a size of point of 16. We want the points to be red with no x-axis label, and so on and so forth. I'm going to comment that just a moment. So this is the block of program that generates that plot. So let's execute it and comment at the same time. So we have in the x-axis the mean in function of index, so from 1 through 20, using the data set results 120. The size of the points that we're using is 16. The color is red. We don't want to have an x-axis that is shown. Then we are setting the limit for the y-axis, for the x-axis, which is going to be the minimum of the lowest value of the confidence interval and the maximum of the upper value. We are also going to set a box around the graphing area. We want an X label that's going to say mean ppm CO2 n equals 120, nothing on the y-axis, and then a title. And so when I execute all of that, we're getting that dot plot here that shows on the x-axis the mean ppm CO2. We have a box around the area. The dots are of a certain size, and the color red. we have the title, and so forth. So now on that graph, we want to add a few more information. First of all, since we want to compare the confidence interval to the mean of our population, or at least what we say, let's assume it's the population, we're going to use the lines function to add a vertical line that shows the mean CO2. Okay, and so here it is. This is the line showing the mean CO2. So here, in this time, we didn't say V equals something, by the way, because we give x-axis values and the y-axis values, right? So the mean CO2 in the x-axis and the numbers 0 to 20 for the y-axis. And then LWG equals 4, that's for the thickness of that line. LTY equals 2, that's for the type of line that we show. Right? For example, we could change that to 1, and now we have a full-on line. Technically, if I want that line to go a little bit further, I could also go to all the way to 21. So now we have a line going through the whole graph. And then we're going to add segments that shows now the span of the confidence interval. So I'm going to use the lower and the upper value for the x-axis, and in the y-axis, just the index. And so here, when I execute that, you see these lines appearing, showing the confidence interval around each of the 20 means that are represented on that graph. And then just for the sort of aesthetic aspect, when I do confidence intervals that I'm showing, or error bars that I'm showing on the graph, I like to have an end to the segment, like a vet. In that case here, since we have a horizontal line showing the confidence interval, I want to have a short vertical dash at the end of it. So I'm going to use the segment function here to add a small little dash at the end, lower end of each confidence interval, and then the second one to represent the other end, the maximum end of that confidence interval. And so now here we see 20 confidence intervals that are represented. So now we can spend some time looking at that figure, but if you look here, we have 2 confidence intervals that don't go over the mean, right? So these are random samples. So because they're random samples, that means that sometimes we're going to have 0 sample out of 20 that do not cross the black line representing the mean of the population. Sometimes we're going to have 1, sometimes 2, and etc. And every result is possible, just with different probabilities. If I would re-execute the program to generate a new set of 20 samples, and then make a new graph out of it, now this time around, so we have 20 new samples, and at this time, each confidence interval crosses the line that corresponds to the mean of the population, or at least the mean of the data set we use as if it would be our population. So what does that mean to us? What that means to us is a confidence interval represents the area within which we have a fairly good confidence that the mean of the population is located. Again, how did I calculate that confidence interval? The lower and the upper value, I used the normal approximation. So I did the mean of the given sample minus or plus 1.96 times the standard error of the mean. Okay, that's how I calculated these confidence intervals. This here would be valid only if our data set is really the population, and therefore we know the standard deviation of the population, we know the size of the population, and things like that. In reality, often we don't know that, so there are other ways to calculate these confidence intervals, but the principle is the same. What we're saying here, when we calculate that confidence interval, we're like, hey, we have that one sample. We think it's an okay representation of the mean of the population, but we want to be a little bit more prudent. And we want to, instead of giving a point estimate, we're going to give the area where we think we have 95% chance that the mean is within these boundaries. The mean of the population is within these boundaries. That's what the 95% confidence interval represents. Let's execute the program to create 20 new samples. Okay, so now we're representing them here, putting the line for the mean of the population, the lines representing each of the confidence intervals, and then the ends for this confidence interval. And now we see this time we have another set of 20 samples, and this time there is 1 out of 20 that does not match that. So if we look just on this graph, 1 out of 20, by the way, times 5, that's 5 out of 100. That's 5%, 95% of them cross the line on that figure. If we put all the figures or the 60 samples we've now created or generated, we had actually something, this time it works. Sometime if you do 3 samples, you might have a little bit less or a little bit more than 3 out of 60. But overall, if you repeat enough samples, the idea again is that 95% of the time, confidence interval will contain the mean of the population. And that's what we call an estimate. Instead of using a point estimate like the mean of the sample, we assume it is bang on the real value of the population. We say, well, we know that when we do a sample, there is some error, the sampling error. So let's use that to say, hey, we acknowledge that the value, the point estimate we have is not exactly the value of the population, but it's close enough. And by the way, we want to be really prudent and say, hey, we think we have 95% chance that it's between this value and that value. That's the upper and lower confidence value. All right, so this is the end for this video.